People have looked for centuries up to the heavens, wondering about the origin and physics behind it all. Have you ever thought about the origin of the aurora borealis, for example, or why astronauts at the International Space Station observe light flashes even with their eyes closed? This is the work of cosmic rays. Cosmic rays were discovered in the early 1900s. At first, scientists believed that it were gamma rays coming from the cosmos, hence their name. But later became clear that most of them were protons or hydrogen cores. But also heavier nuclei, like helium and iron, are part of the cosmic ray spectrum, traveling at enormous velocities in all directions. To obtain such velocities, high energetic events in the universe are needed. One plausible object could be a dying star, massive enough to end in a big explosion, a supernova. A supernova produces shock waves where particles like protons could be accelerated up to very high velocities. Also, other sources like active galactic nuclei or black holes and pulsars were suggested, but their contribution remains still unclear up to date. From these sources in the galaxies, the cosmic rays travel towards the Earth, but research has shown that they reside at least 1 billion years inside the galaxy before reaching the Earth. The ultra-high energetic cosmic rays are even believed to originate from outside our own galaxy, coming from other galaxies. When cosmic rays enter the Earth's atmosphere, they collide with air molecules, resulting in the production of all sorts of particles like protons, ions, muons, electrons, kaons, and many more. But how do we know they existed in the first place, those cosmic rays? To measure them directly, the cosmic rays need to be catched before interacting with the atmosphere. Therefore, satellites equipped with particles detector have been launched into orbit around the Earth. But also balloon experiments are able to do this, as they reside high enough in the atmosphere to intercept the primary particle. However, when particles become too energetic, large volumes are needed to stop them, which is impossible. For satellites and balloons, and indirect measurements at the surface of the Earth are our only option. As cosmic rays travel downwards to the surface, they collide with molecules, resulting in the production of more but less energetic particles. These particles travel further downwards and will collide again, resulting in the same process, generating more and more particles over and over again. This is called a cascade or air shower. During the cascade formation, the particles also transfer some energy to the air molecules, who will, in their return, emit it in the form of the photon, or light. This is called fluorescence, and is the same process which produces light in fluorescent lamps. This radiation can then be detected using telescopes at the ground. But as these secondary particles travel further downwards, they will at a certain time encounter the Earth's surface. Some of those particles will even be able to travel into the surface. As Einstein declared, the speed limit of the universe is the light speed in vacuum. However, in a medium like the Earth's surface, light can slow down and particles can travel faster than the light in that medium. When this happens and the particles have an electrical charge, they radiate a bluish light, called Cherenkov radiation. It is this phenomenon that produces light flashes inside the eyes of astronauts, making it possible for them to see light even with their eyes closed. But it also happens in the polar ice at the South Pole. Putting light-sensitive detectors, or digital optical modules as we call them, DOM for short, putting them in the ice and in tanks filled with ice on top of the surface enables us scientists to detect the Cherenkov light emitted by particles and therefore the presence of such high-energy charged particles. The array of tanks on top of the surface is called IceTop. The domes deployed in the ice form IceCube. IceTop consists of 81 stations, of each 2 tanks holding 2 domes. This makes 324 domes distributed over 1 square kilometer. IceCube consists of 86 strings, each holding 60 domes, making 5,160 domes watching the ice, looking for flashes of Cherenkov light. Together with IceTop, IceCube forms the IceCube Neutrino Observatory, monitoring the sky for astrophysical neutrinos and cosmic rays. The signals from this detector are then processed by the IceCube lab, a giant computer server at the South Pole. It selects the interesting signals and builds them into events, ready to send them to the headquarters of the observatory in the Northern Hemisphere. But to be able to interpret these data, one needs to have a good understanding about the physics behind it all. This is where simulations come into play. Using a model, virtual data is produced by simulating the different processes in the atmosphere with a supercomputer. However, multiple models exist, which result in all slightly different data-like files. For my master dissertation, I compared these different models and looked at the differences they produce in signals. And although this analysis may seem small, I believe it will contribute and bring us one step closer to answer more unresolved questions about cosmic rays. This video was made in context of my master dissertation at the University of Ghent to obtain the Master of Science in Physics and Astronomy. I did my master dissertation in the research group of experimental particle physics with as promoter Professor Dirk Ryckbosch and under the supervision of Alessio Porcelli and Stef Verpoest. If you like this video or want to see more, give this video a big thumbs up, comment below, and don't forget to subscribe. Till next time!